Hello.
Hello.
Hey, hope you're doing well. How's your day going?
My day is going fine.
Awesome. All right. So just to get us started, maybe give me a quick overview of what you're prepping for, as well as what you're looking to get out of this. At least, in this context, given it's Microsoft, maybe also like give me a sense of like the teams and all that. I might be able to like have specific questions that help you.
Okay. I'm just mainly doing an interview practice session just to keep fresh on technical interviews for programming.
Hmm.
That's primarily all there is at this point. I don't have any interviews currently scheduled. I just want to make sure that I'm up on keeping practiced with stuff like this.
I see what you're saying. Okay. And how much experience do you have with this liquid type of questions or coding interview type of questions?
I have a decent amount of experience with these questions. I've had a few of these practice interviews in the past, and I've also spent quite a bit of time working on questions like these on my own.
I see. Okay, that's good. And so, given at least your own practice, do you have a sense of, let's say, a specific type of pattern that you struggle with? That way we can at least focus on that rather than give you something that you're already good at.
Um, I can't think of anything in particular now.
Okay, sounds good. Okay, then cool. I'm just going to carry my heuristic again. I'm going to use what I have observed at Microsoft. So there tends to be, there usually is a tendency towards array problems as well as tree problems. And I feel like tree problems might be something worth exploring at the moment, especially since I feel like the practice with setup and traversal is usually a good thing. So maybe we can focus on that. Are you okay with that?
Sure.
Awesome. All right. So you wanna select the language you wanna use?
Which language we're going to use of what you said?
Yeah, like feel free to select the language. You can switch it
Okay.
up at the top. Awesome. All right. So interesting. It's been a while since I used C sharp in this case, but that's cool. So what we're going to do here is we are going to try and solve this particular problem here. So you'll be given a tree, and what I want you to return is the maximum sum of leaves from the left to the right. So let me actually comment this out here. I don't know the syntax of commenting in C sharp actually. Okay, that works. So the whole idea here is if you're given a tree like this, so let's say this is our leaf node here, and let's say we have 2 right here, and maybe 5, and maybe here it's 10. So in this case, the maximum sum from root to leaf will be basically 2 plus 5 plus 10. So that should be 17.
Yeah.
Does it make sense what the question is trying to do?
Yeah.
Awesome. So I would like to see you just resolve this, and then if you can solve that, we can always extend it even further. So I have some extensions that you can always look into.
Okay.
I'm going to
Uh,
type with this.
total sum of all. Okay, so all root to leaf numbers, so we are going to include 5 in there. First time I read it through, it sounded like we were just checking on the leaf numbers.
Uh, so like in this case, this example here will look something similar to this really, but it's basically uh, right here. So let me give you the full picture here. So 2, 1, and 3. So 2 to the left here, and then so it's not necessarily a balanced binary tree here. So it's like a normal B tree. So
Okay.
2, 1, 3 here.
Okay. And one thing is, it sounded like the root to leaf path. So root to leaf path 123 represents the number 123. So is that the specific sums that we're trying, or is that specific sums we're trying to do, or are we doing the summing that you mentioned?
No, no. So yeah, so that's the specific sum that we'll be attempting to do in this regard. So in this case,
Okay.
yeah,
So we do want to move tens place around based on the leaves.
exactly.
Or, okay. Uh, okay, so we're going to probably do some notepad stuff here. Just a minute, I need a better angle on my keyboard. So what we're probably going to want to do is to find the values at these sort of leaves. First, we're going to start at the root, and we're going to keep track of uh, the current sum we're at. Sum is 5 to a leaf. We are going to multiply the previous sum by 10 to move tens place, and add the leaf value. Or that might not be a leaf, but go down a node. We'll just leave it as that for now. Keep doing this until we get to a leaf. And then we are going to, so total sum of all root 2 leaf numbers. So if we have this tree structure right here, where we have 1, down here we end up with 12, and down here we end up with 13, would the total that we're looking at end up being 25, so 12 plus 13, or 26, 12 plus 13 plus the 1 of this?
Actually, it will be some root to leaf, so it will be 12 plus 13. So this should be 25.
Okay, so when we count the totals, we only count the value that we have once we've reached the leaf node.
Exactly. Yeah. And
Okay.
in the case where, let's say, we have an input like this, where let's say it's only 1, and let's say actually maybe this is what I'm thinking about. So let's say, I don't know why the heck typing is becoming a bit of an issue here. So what if we had like a 1 and maybe just 2 here? So it has no left children here. What do you think that should be?
That should be 12, because since we don't have a left child, we're not going to, or actually, yeah, it should be 12, because 2 is going to be the only leaf node.
Exactly. So that the key bit right there is knowing what a leaf is, right? So we are not considering anything that might have children.
Yeah. Keep doing this until we get to a leaf, no children. Then add the sum at that leaf to the total. And then just keep navigating the tree until we have all sums. Okay. So I think that covers the majority of what we want to do here. We probably want to set this up. I believe recursively is generally the way that we're going to do things for a tree. Just makes the most sense, and we're going to have to pass in the previous sum and the node we're navigating to. Okay. So I think that that's pretty good. If we wanted to do if we wanted to write out the full thing in pseudocode, we could do that right now, or I feel comfortable enough with this that we could move to writing it out in C# directly. One thing I actually do want to ask is, are we going to have to write this tree structure ourselves?
Yes, that's actually the other bit. So yeah, we will be defining the tree structure. That's actually one of the things I wanted to see you do. But yes, so feel free to do it as you please. I've seen some people using dictionaries, some people using class structure, so it's up to you.
Okay. Yeah, I would probably end up using a class for this. So I think I'll probably just move to the coding, because what we've defined here is pretty simple, and we have this sort of basic outline of this, although it doesn't have the exact architecture of what we're doing. We're going to clear out this main. This main is going to call our function, but first we want to get that tree node class. So class tree node. I'm going to need to define. So we're going to have our public tree node left. Public tree node right. I do not remember if we need a constructor, but I might just put one in for clarity. We're also going to want to make these nullable. Unless this particular one doesn't like this. Well, annotations context, okay.
So I think we probably also need a value because it's fundamentally left, right, and value, right?
Yes, we are also going to need a value. And we're always going to have a value. Our public tree node int val. Value equals val. We'll just add our. We can just add. No, it will be very simple to just make a quick. Just name these simply. Okay, so the only thing that I have noticed is I believe the environment I usually use handles this nullable problem that we're having right now. So nullable annotations context.
Yeah, maybe try tree node left equals to, we can initiate it as now. So instead of like making it optional here, we just, can initiate it as now.
Okay, and it doesn't have any issues with that. Okay, so I can probably remove these.
All right.
No, and then I know that that's fairly simple to go back and fix if the environment works this particular way.
Awesome.
So what we're probably going to want to do is we're going to build our input tree. So let's just do our 1, 2, 3 example for the moment. A. We'll just do these in line because we're only doing a couple. And then we are going to Why am I blanking on this? I haven't used println in a while. Okay. Main thing, let's just get the call in place first, and then not worry about something like that just for the moment. So our call for the moment is just going to be we're just going to call this leaf sum, and we're going to give it input tree A. static int sum tree node root. So we're going to call into this one. Oh, it just doesn't like that we don't have a value. So what we're going to do is we're going to call a different version of leaf sum in here that we can call recursively a bit nicer. So we're just going to pass it in the root, and then we are just going to pass it in an integer. Tree node root int rev total. Okay, so now we have the actual sort of environment that we're going to be using. This might need to be... no, that should be fine. Okay, so when we get into this, we're going to have a tree node. We're going to have 3 different possible...
So just my understanding in terms of naming convention. So this right here, these 2 functions here. So you have leave sum right here. Sorry, can you hear me?
Yeah.
Hello? Can you hear me?
Yeah, I can hear you. Can you not hear me? Hello? Uh-oh. Can you hear me?
I kind of lost you for a second there. Are you able to hear me?
Yeah, I can hear you.
All right, sorry. I was asking right here, so for naming convention here, so we have leave sum right here, which is going to be calling the function, or at least initiating the call here, and it initiates it to the previous sum as 0 right here.
Yeah.
And then this right here basically is going to now be the generic function here, and so it's going to be the one that's actually making the recursive calls, right?
Yeah.
Awesome. All right. So are we able to maybe rename this? Because, it's essentially the current node, not the root. It's not always going to be the root, right?
Yeah, that's a good point.
Yeah, and same case with the function.
Sorry, I didn't hear that.
Like, yeah, I think you might also want to rename the function. That way, at least we know, what it's doing, right?
Sure. Cursive, and then I believe because this is C#, it wants us to capitalize. Wait. Oh no, it's just complaining about code paths.
Yeah.
Okay, so we're going to have 3 different possible situations that we run into when we get here. What we really want to check first is if our if these are both null. And then this is going to be our base case where we've reached a leaf and we can sort of return our previous sum. So, or we're going to return our current sum, which we'll calculate up here. Current sum will just be, I referred to this as total earlier, so we will change that to total. So current total is just going to be previous total int. Oh god. Previous total times 10, and we are going to add current dot value to it. Okay, so if we don't have either of these, we're just going to return our current total. And then, let's see. Okay, yeah, that's completely fine for there, and then we handle the other stuff when we get down to here. So we have at least something that isn't null. So if current dot left is not equal to null, that means we have a current dot left that we can work with. So we are going to do so we're going to make a result here and initialize it to 0. So if we have a left, we're going to do results plus equals a leaf sum recursive on current.left, and then our prev total is going to be our current total in here. Then we just do the same thing for the right path.
Okay. So let me just for my understanding again. So right here is, so in this case we're checking if we've hit the leaf, and then if we ever hit the leaf, we return the current total.
Yeah.
And then for these two, what we are doing is we're essentially percolating down. Actually, it's not percolating. It's actually going down the tree to find the leaves, right?
Yeah, we're going down the tree to find the leaf.
I see.
And then, oh yeah, go ahead, sorry.
Yeah, so the way I'm thinking of it here is you have the values that you're exploring. So at any given point, you have a node, you have a current node, right?
Yeah.
And so that node has a value, and you want to be attaching that value, like building it up from the top. Because what we saw was, if we have, let's say, the 1 to 3 example, we are coming from the top, we have 1, and then we have the 2. If we add any more, we basically are like attaching them. So it's kind of building itself as we go, and then as soon as we hit the leaf, we have a value, and that's what we add.
Yeah.
Right? And so what will the result really do for us here, like this result right here?
So this result is basically, that's our way of passing up the, so each time we reach a leaf, we get one of the numbers that we're going to add into the result that we finally get from the entire function. What this result does is, if we have both a left node and a right node, we're going to need to get the numbers from both of them together and then pass that back up the tree. Yeah.
Excellent. Okay, that makes sense.
Okay. So once we get those, that should be enough to just return the result as is. That will keep traveling back up the tree. I believe that should be all that we need to do to get a basic run, except that we want to do a quick print for this. Yeah, so that was just console.writeline. That, and let's see what we get running this the first time. Okay. Okay, so we have the nulls that we just need to change. So that is, what did I say? Okay, yeah, we just need to make these nullable here, and it probably wants them on 40. Yeah, 47 and 42 are the only issues. So we're going to do that, and then it will probably, oh, no, wait, it ran. Okay, yeah. We just needed to change that for semantics. Okay, so it looks like this works. So what we probably want to do now is to start running some tests just to make sure that things work properly. Let's make sure, these should be very simple, but just doing quick check to make sure that it will handle these properly. Node 3. Okay. So those seem to be fine. We're just going to leave this one here, and let's make an input tree B. So now we should probably test some more complicated cases. Actually, one really obvious case that we should definitely test is what happens if we just pass in the root. Whoops, I need to rename this. And that looks like it works fine.
Mm-hmm.
Okay, so let's do something a bit more complex. What is a good thing to test for this? We should probably test that. We should probably test a tree that has leaf nodes that aren't all on the same level. So I'm just going to do. We'll just make a quick text representation up here of some of the trees that we'll be testing.
Actually, you can just write them out without the slashes. I know they're like they throw people off in that
Okay.
case. Yeah, I've noticed they are really hard to work with.
Okay.
Yeah, that's
So we
easy.
have that. So we should probably have something more along the lines of this, where we should probably also have something more along the lines of this, just to have, and we'll just put nulls, or well, those will just be empty. So that we have different, so we have roots on different levels. We can just work this out really quickly. So 124 plus 125 is going to be 249, plus 13 is going to be, that's 262, yeah.
Mm-hmm.
Yeah, we will do a quick separator above these just to put in the value that we're expecting. Okay, so let's build this tree. So we're going to do new tree node. We're just going to put in a null for now, and then new tree node 3. We are going to do tree node input tree BL. It's going to be the left side of this tree that we're just going to put here so we don't have a really, really long line. Okay, so that should be correct. We just need to do input tree B dot left equals input tree BL. Okay. So let's run this and see how it runs. We got 262. Okay, so that looks like it runs good. The only thing that I will change for the moment is we'll have the same output. We're just going to put this on the right side just to make certain that it handles it on the right, although I don't see any reason why it would not.
All right.
Okay. I think that this seems pretty good. I can't think particularly of any other cases that we'd want to test for, other than it's mentioned up here that the inputs that we get should all fit into a 32-bit integer. So, and that's just as a matter of test cases, and that would basically be the only thing that I would think of for testing at the moment.
This should be good. Yeah, I think yeah, this really works well. And I was actually just laughing at myself looking at the output. It even it says your name recursive snow. That's your alias, and I'm like,
Yeah.
yep, clearly he got the recursion done right here. So really good work right there. So maybe talk to me about what the complexity for this is, both time and space.
Okay, so complexity, I need to think on for a minute. Complexity for recursive stuff is something that I do not have directly on the mind. When it comes to space complexity, though, this is pretty lightweight. We basically just have, because we have our input tree, and then all we're really doing is we're just using like a handful of integers that to tally our results. So it's basically we're going to have an input complexity of like, or the complexity of like O of 1 for extra space, since our input tree is not going to be counted.
Mm-hmm.
And then when it comes to the time complexity, that's probably just going to be I think that should end up essentially working out to O of n, because we are going to be just visiting every single node in the data once. We don't have to revisit anything. It's just going to work out to be, yeah. Trees grow in a bit of a weird way, but when we're considering the raw number of nodes that are going to be in it, it's just going to be O of n for runtime.
All right.
I believe.
Yeah. Yep. That sounds about right here. Because at the end we kind of have to explore all the paths really from the root to pretty much all the leaves. So it's actually over, and so that's good. And yeah, you're right.
Okay.
We fortunately, the way you implemented it is what really works well here. Like we're tracking the sum as you compute, so it's actually going to be just single memory for each recursive call. So it's all of one. So that's good. And so, okay, so this is good. Analysis is spot on. Every implementation is spot on. So let's actually tackle the harder variant of this question. So what if instead of the total sum, we were interested in the maximum path sum? And by that, what I mean is, if say you look at, let's say, the third example, this one right here, on line 63 to 65. So the maximum path sum for us would be from 5 to 2 to 1 to 3.
Yeah.
So that's kind of like left to right path sum here. So how would you compute that? So that's kind of the next step with this.
Okay. So what we're probably going to want to do is there are things that we could look at with this, such as basically, because we don't know the exact structure of the tree, we know that we can't really throw anything out too early, unfortunately. Because if we knew that all of our nodes down here were going to be populated, like if we knew 100% that we had a 6 and a 7 here, when we're at this one, we would have to choose, or we'd have 2 or 3 next. We could cut down on time. We could cut down on quite a lot of time, because if we knew that all of our leaves are on the same level, that exploring the 2 path is pretty pointless, because everything on the 3 path would be larger. But we can't make that optimization because we don't know, or not all of our leaves are on the same level. We're going to have some leaves that are further up, so we're going to need to fully explore.
And I'll note the one bit here, and this is actually the intent. We're not calling it a BST. It's not a binary search tree, because you can see we have a 5 here, which is smaller than a value on the right side. So
Yeah.
it's really not about that. Like we cannot make that assumption that anything on the right is always going to be larger, right?
We can with this particular setup, though, because if we know that, because we have 1 here, and then we get to 12, and then everything down here is going to be 120 something. But we would know that everything on this side is going to be 130 something, so we know for sure that this side would be larger. It's just a matter of we can't make that particular optimization because we might not have all leaves on the same level.
So
Which
sorry.
means we do have. Ooh.
Yeah, the bit I was clarifying. So okay, let's actually maybe
Yeah.
I don't understand that fully here, but okay. So if we are at 1-3, so we know it's 130 something, right?
Yeah.
And so how can we, like in this case, it's possible that we could have 137 and this is the one that's 136. Like they can be flipped. It's based off of our setup. It's not a BST. It's a binary tree. So just two-way in this case. And so it's possible that the left child here can be larger than the right child.
Yeah, it's possible that this, because what we're talking about when it comes to the sums, because the actual sums that we're looking at to find the best leaf node involve everything that's further up the tree as well. Because this node represents 137, not just 7.
Indeed.
Yeah, which is why, because when we get to here, we do have to check both of these just to make sure, and we're at the leaf level, so we know that whatever we have down here is sort of our final answer. But when we're up here, we do know that all of the leaf nodes down here, because this previous tens place exists, are going to be all larger than these ones because of this previous tens place. Because
I see what you're saying. Okay.
yeah.
All right, that makes sense.
Yeah. So but that is one optimization we can't make, because if we had a tree like this, we would just throw out the other side and we would end up with an answer that's only 13, which is very much not correct.
Exactly.
Yeah. So what we're probably going to want to do is, since all we need to do is find the maximum, we don't want to use much extra space and then have to sort of navigate the extra space that we do have. What we probably want to do is, the easiest way would be to have some sort of class member. I think ideally we would have a separate class for everything that calculates our leaf sum and everything, but for convenience sake, we're going to we're just going to set up out here in solution a sort of class member variable that we'll just use to calculate current max. And we'll initialize this to 0. So we can access current max from basically wherever. So now that we have our new goal, we can we can modify some of this just to, we'd probably not want to return these ints. I'll just leave them in here. We're doing a bit of extra work, but we don't really need to worry about them. So we're going to add another write line that will get us our will get the value of the maximum path. Actually, that is an important question. Do we want the value of the maximum path?
Yep. So yeah, we're interested in the sum of the maximum path in this case. So I mean, it's kind of different to what we've been calculating in this case. So it's not gonna be 125 plus, let's say, 13. It's gonna be the 5 plus 2 plus 1 plus 3, right? So we actually want the individual values in this case. But I think they're kind of related, because honestly, if we have 124, let's say, although that's actually a good question, because 129 might be bigger than 125. Actually, no, that might not be the case. Sorry, I meant 129. In this case, I'm actually evaluating if we had, let's say, an objectively bigger value, like, is its sum strictly bigger? Because when I think of it, 129 might be smaller, or might be bigger than, let's say, 131. But at the same time, they have a shared core there, so that's not really a possibility. So that kind of is fine, but it will be up to you. That's all my thought process at the moment.
Okay, so yeah, what I think that we're going to do is, we have this current max that's just going to keep track of the sort of maximum value that we found at a leaf node, and all we really need to change here is when we get down to here where we have, okay. So all we really need to do is we just need to change this part right here. We should label these just to make this easier. I've been coding with Python. Okay.
Oh, yeah, you've been coding with Python?
I've been doing Python practice recently.
Fair enough, yeah. In my case, I have a Python background, but I've actually been practicing C# myself, so opposite routes.
Yeah. So we're going to just do leaf / base case, and then non-leaf. Just to keep easier track of those, let's just add an extra line to make that look a little bit less messy. So all we're going to do here is we have our current total here, and we know we're at a leaf node. So basically all we want to do is just check if current total is greater than our current max, then we're just going to change current max to be current total.
That's good. So you're using a global variable in this case that can be modified by any of the recursive calls, right?
Yeah, just because that's going to be the easiest. It's going to be the easiest way, or it's the least modification we'd have to do for the code. If we didn't want to use that, it would be possible to pass this stuff around, although it's not really that convenient. We'd have to change quite a few things, but if this is within sort of the realm of what we want to do, keep track of things with a class variable, then that's probably the best way to do it. We should also run this just to make sure it's working properly.
Yeah. And mind you, keep in mind the bit that I pointed out on, we want the sum of the individual values, not the sum of the part itself. So that's the only thing to be mindful of here. Okay.
Oh, okay. So we would want. So when we're comparing this part, we're adding 1 plus 2 plus 4.
Exactly. Yeah. So it's 1 plus 2 plus 4, 1 plus 2 plus 5.
Okay. Okay.
Yeah, and that's kind of why I went on that tangent, wondering, okay, let's say 130 bigger than 129 or something. That's kind of why I was asking myself that.
Okay, yeah. Okay, so that's a bit different. So first off, we're going to need to modify this to also keep track of a max total as we're moving through these. No, I do not. So our max total will just keep track of the individual numbers. We don't modify, or we don't multiply them by 10.
Mm-hmm.
So int current max total is just going to be max total plus current dot value. Okay, and now first thing we're going to do is current max total, change these to the right numbers, and those are good. We need to fix these calls down here to use current max total as well.
Mm-hmm.
And I think those are the primary changes that we would need. That should carry through everything properly. Let's run it to double check. Or actually, let's also just do a quick add something up here to give it the output that we should end up with. So this should end up with 4. This should end up with 5, 6, 7, 8. Okay, so that works out. We should probably add a new test case just to double check. Like, let's just do something like this. 1, 2, 1, 2, 4, 5, and then over here we have 9.
Mm-hmm.
This, we should get 124. It's basically just the above plus 6, so it would be 200 and plus 6. Yeah, that's correct. So that would just be 268, and then 10 should be our other value. So let's make this tree down here. This will be our tree C. We can just copy all of this, actually. Left. And we just need to change this to 9. That should all be right. Let's run this. So that should be 268 and 10. Something happened. Let me make sure that's not just me. That's just me putting something wrong in the tree. Okay. Tree node 9. Yeah, I forgot I reversed the left and right on this tree when I copied it over. That should
Right.
be... Yep, that works.
Excellent.
Okay.
Awesome.
So, yeah, I think that covers what has been asked for.
All right. That's good. I think we can call it an end to the interview at the moment. We're on minute 45, which should
Okay.
be the running length for typical interviews. So you did a good job. You did a really, really good job. So I want to start with you in this case. So looking back at the interview, maybe point out to me, based off of your intuition, what do you think you did well and what do you think you could improve on?
I think I did well with sort of handling the problem, writing out my explanation for it. I think it might be a good idea to write something that is a bit more structured pseudocode, although I felt pretty confident with the problem, and we already had this sort of step-by-step up on line 23
Mm-hmm.
written out. So I sort of, in this particular case, I felt like it was probably safe to move on and show that. I think that did pretty well. There was a couple just sort of little organizational stumbles or forgetting one or two things just in the moment because I hadn't been working with C# for the past couple weeks. Those, I think, are the main things I could think of at the moment.
Absolutely, yeah. And so, yeah, I'll tell you this. I'm actually very stunned that you're considered a junior engineer because this is probably one of the top three performances I've seen on the platform. Because what you just did here was solve a medium question and a hard question on LeetCode, all within
Hmm.
45 minutes. So there's no denying that that was an extremely strong performance. I absolutely like your communication style. I feel like, you don't say too much, you don't say too little, and so it was extremely easy to follow what you're saying. And that's why anytime I interjected, you kind of saw it was always incremental, and it was always like fixing a little bug here and there. I didn't try to like ruin your flow. I was really able to easily follow everything you're saying, and I really liked how you started with the pseudocode. You listed out the steps you want to follow. So overall communication extremely good in this case, very well balanced. And then I really liked how you clarified the initial requirements. I do realize that there was a bit of confusion initially on what we mean by sum, because the two types of sum we could calculate. Either we are calculating the running sum or the individual sums. So you really took the time to understand the question, and that was really, really good. Like making sure you understand exactly what you're targeting here. And then I liked how you organized your code. This is good, like splitting it into helper and caller functions in this case. That really helps make sure that there's no confusion. So even the implementation bit, I felt like it was really, really good. Like the variable names are done well. Even the way you set up your test cases. Maybe the only neat kind of feedback that I might give here will be, sometimes, especially if the question is a bit more tricky, at least, or let's say the core understanding might not be there, it might be worthwhile setting up test cases later on after like writing the core logic and basically operating under the assumption that you already have the test done. So that might be the only bit that I tell you, maybe think a bit, maybe set up the test cases later so that you're not taking up time that could use. But in this case, clearly it didn't hinder you, so I really wouldn't hold that against you. But overall, I really don't have a lot of negatives in this case. Like this, as I said, this has been one of the best performances I've seen. So if you have interviews going knowing that you're gonna nail them. So this was a really, really, really strong performance. And so for context, these are the two problems. I'll even share them right here. So on line 141, that's actually one of them here. I believe that's the medium version. And then this is actually the hard version. And keep in mind, these are actually questions that I would ask people, and a lot of people really struggle with them. And so the fact that you're able to solve both of them in this one session, that was actually really, really good.
Okay.
Yeah. All right. I don't know. Have you seen these questions before, just out of curiosity?
I don't think I've done the medium version, but I do think I have done this hard version in the past. But also, I had a lot of coursework that was working with binary trees. That was something
Right.
that they really wanted us to be confident with.
Absolutely. Like clearly the practice paid off because yeah, as I said, this was impressive. So really, really, really good job overall. Okay.
Okay, thank you.
Absolutely. I don't know if there's any other questions, anything I can clarify. I know it wasn't like critical or anything, but hey, if you did well, you did well. So there's not much I can say about that, right?
Yeah.
Yeah. Any questions? Anything I can clarify for you? Any questions related to, let's say, Microsoft or the likes? Is there anything you want to know?
Um, Maybe I think not particularly that I can think of. Actually, one thing that I would want, er, no, I don't think that would actually come up here. Nah, never mind. There's not anything I can particularly think to ask. If I remember correctly, it's been a while since I've done an interview on this site. There is a way to contact you after the interview, right? If I did want to ask any follow-up questions, just because I'm
Yeah,
blanking on any possible ones here.
yeah, I'll set my contact up. So I'll just set it such that you can easily reach out both on LinkedIn as well as email. So I'll make those options available in the feedback form. And actually, if you don't mind, given how strong this performance was, maybe if you're comfortable, we can showcase it because I feel like people can learn from this. Like this is what I would like to point out to when I'm telling people this is how you do an interview. So if you don't mind, we can like set it to be showcased. I think that'll be helpful for both us and the community.
Yes, I can do that.
Awesome. All right. Yeah. So yeah, I'll leave my contact. If you have any question, feel free to reach out. And yeah, as I said, like this was honestly really really fun. Like it's usually rare where you go into an interview and then you come out of it, you're like, I'm glad I met that person. So really really you did a good job in this case. Like an excellent work overall.
Thank you very much.
All right. Anyway, all right. We can drop off for now. But yeah, feel free to reach out if you have any questions. And yeah, good luck with any interviews you'll have coming up. Okay.
All right. Thank you.
All right.